Okay, so we will start with the class. So in the previous class, we have gone through the basics of the JFET, that is the junction field effect transistor. So in the previous class, we have gone through the, the construction and the working of a JFET. So now next we will see some of the equations or the mathematical expression and analysis in terms of the JFET, like how the current is defined in case of JFET, and also we will see different parameters associated with the JFET. So this is all that we have covered in the previous class. So we will be starting with uh, the current equation in case of a JFET. Okay. So we have seen here. Okay. So this was the transfer characteristic. Like we will be plotting the ID, that is drain current, with respect to the input voltage. So input voltage is our VGS. So this was the plot. So when VGS is 0, at that time the maximum current will be flowing, and with respect to that it will be keep on decreasing as we are going to reverse bias the gate to source voltage. Okay. So this is your region called saturation region. So why it is called saturation region? Because the current in this saturation region is constant. Okay. So this is the output characteristics, or we call it drain characteristics. So here the current is constant, so it is active region, or we also call it saturation region. Active or saturation, and this region is called your ohmic region. So below this we are calling it cutoff region. Okay. So below this it will be cutoff. So the JFET, we can say it is going to work in either cutoff or ohmic region or active or saturation region. So basically when we are going to have a amplification application, we will be making sure like the JFET is going to be working in active or saturation region. Okay. So we will basically deal with the saturation region or active region only. So how the drain current is defined in case of saturation region, we will see that. So drain current, that is ID, that is basically given by the equation ID equals to IDSS 1 minus VGS divided by VP. So this is VP, that is VP, that is called pinch off voltage. Okay. So this is the current equation in case of JFET, and this current is equation is also called the Shockley equation. This current equation, this equation is called okay. So the drain current of JFET is defined by the Shockley equation. So it is related like ID is related to IDSS. So this IDSS is the maximum current that can flow through the JFET when VGS is equals to 0. Okay. So this is we can just see from the transfer curve also. So this is IDSS, or this is the current when the pinch off has occurred. After that, the current will be flowing is IDSS. So with respect to transfer characteristics, we can say this IDSS is the current when VGS is equals to 0. This is with respect to transfer characteristics. With respect to drain characteristics, we can call it like, so this is your IDSS this occurs when VGS equals to 0, and this is the point of pinch off. So beyond pinch off, whenever we are going to increase the VDS, whatever current will be flowing, that will be your IDSS when VGS equals to 0. So this IDSS is defined only for VGS. When VGS equals to -1 is there, and this is the constant current. So this constant current is not equals to IDSS. Okay, so it will be some value of ID, but it will not be equal to IDSS. IDSS will be the current defined only when VGS equals to 0, and at that time when pinch off has occurred, whatever current constant current is flowing, that will be your IDSS. So in both the cases we can just see. So this is where VGS is 0, at that time whatever current is flowing. So that is your IDSS. And 1 minus VGS, get to source voltage, divided by VP. So this VP is your pinch off voltage. So pinch off voltage is the point after that the current becomes constant in JFET, or this is the point, or this is the minimum value of VDS. This is the minimum value of VDS for ID becomes equals to IDSS. Okay, so what is the minimum value of VDS at which the ID becomes IDSS? That will be your pinch off voltage. Okay, so here this ID is related with square of 1 minus VGS divided by VP. That means it is dependent on square of VGS voltage, we can call it in one respect. Okay, so we also call it this Fvts, we call it like Fvts are a square device, because the voltage and current equation is defined by, or you can call it the current is defined in terms of square of the voltage. That's why it is called a square device. Okay, and also here, if we are going to increase the temperature, then what is the relation with respect to the temperature and ID? So temperature versus ID, if we are going to plot, so this will be like when we are going to have, because in BJTs, when so we are going to increase the temperature, the majority carriers were almost constant, but the minority carriers were increasing very rapidly. Okay, but in case of FETs, there is no minority carrier. Okay, so here one thing we can note, the majority carrier is constant. Suppose we are increasing the temperature. Okay, so at that time majority carrier will be constant, and the minority carrier is not available, so we will not be talking about minority carriers. But if we talk about the mobility, okay, so mobility of charge carriers is going to decrease as we are increasing the temperature. So we have previously in the previous classes, starting classes, we have gone through the variation of mobility in terms of temperature. So mu is proportionality with a factor of m, that is mu is directly proportional to t to the power minus m. So this m varies with respect to it is m is a proportionality, I could say the proportionality constant is there, or construction parameter, that is based on the type of uh, construction that we are going to have. So this m value depends on uh, different parameters. Okay, so it m values varies between, like, it is 1.2, 1 or 3.2, that means 0.5, 1 and 1.5. Okay, so these values are varying. So with respect to this m values, this mobility varies. So here in one terms we can call it like the mu is going to be a inversely proportional to temperature in one terms, because it is minus m, so it will be inversely proportional to t to the power m. Okay, so as we are going to increase the temperature, the mobility will decrease. So as mobility is going to decrease, the current will also be decreasing. Okay, so this temperature, if temperature is going to increase, the current ID will decrease. So this decrease will be because in decrease in the mobility. Okay, it is not because of the magnetic carrier relation, because there is no magnetic carrier in FATs basically. So this is the current equation and the variation of current with respect to temperature, and it will be depending on the gate to source voltage. Okay, so next we will see that how the pinch off is going to have the relation. So ID depends on pinch off also. Okay, so how this is depending, we will see that. So in the pinch off relation, when VDS is equals to pinch off, at that time we have seen like the channel width is going to be a 0. Okay, that means when channel width is going to be 0, at that time the current is IDSS. But practically it is not like channel width is not going to be a 0. So at that time the channel width reduces very much, but it is not equals to exactly 0. So there is some space available between the two depletion regions. So as we are going to increase the VDS, there will be high electric field intensity in the channel region. So because of high electric field in the channel region, there will be very high current flowing when the depletion regions of two gates are going to touch each other. So it will not be touching. That means the width will not be equals to 0, but it will be some value, like it will be very small, and through that very small gap or very small channel width, there will be a current flowing. That current will be very high because of high electric field intensity that is generated because of VDS. Okay, so there is a conflict of interest, we can call it like. So sometimes we call it VP, that is equal in magnitude with respect to VGS off. So we have seen in the previous class also, this pinch off voltage is equal in magnitude with the VGS value when the VGS is going to cut off the device. Okay, so VGS is going to cut off the device. For this, the condition is, so VGS we are applying is VGS off for ID is equals to 0. So this is the relation when VGS off is defined, and VP is the relation when VDS we are applying, such that we have the ID is equals to IDSS. Okay, so what we frequently call like the VP and VGS will be of same magnitude but in opposite direction. Like if VP is positive, then VGS will be negative. So here VP is of opposite sign with the VGS off. So once we have ID is equals to IDSS 1 minus VGS by VP to hold the power 2. From there, if we want to find out the VGS, what is gate to source voltage, that will be by transferring, we can just get VP multiplied by 1 minus under root ID divided by IDSS. So this is the relation of VGS. So these two relations are very important for defining. So the characteristics of JFET. So this is one of the relations. So based on these two relations, the questions related to numerical questions will be asked very frequently. So if we can remember this ID equals to IDSS 1 minus VGS by VP to the power 2, that will be going to solve all the questions related to the JFET. Okay. So here sometimes like IDSS and sorry, this VP and the VGS is defined. So if this is the condition, if we see from here, if we put the value of VGS equals to VP, suppose we are going to put VGS is equals to VP. Okay. So if we are going to put VGS equals to VP, from there we can say like if we are going to put this VP is equals to VP 1 minus under root ID by IDSS. So this is like it will be cut. So it will be 1 equals to 1 minus ID divided by IDSS. So this will be like this. And then from here we can just write like ID will be nothing but the 0. Okay. So it will be like ID is equals to 0 from there. Okay. So this ID equals to 0 is the case when the JFET is in cutoff region. Okay, so when we have put VGS is equals to VP in the equation defined by the Shockley, that is Shockley equation. So here VGS is equals to VP. If we are putting this, then by putting this value, we can just see uh, ID is going to be 0. That means this is the condition for JFET to be in cutoff region. So we can just see like this. This is like VGS is equals to VP, but this is the case when VGS should be equals to VGS off. Okay. If we are going to put this value, we are getting ID equals to 0. But this ID equals to 0 is the condition when VGS should be equals to VGS off. So from these two, we can just conclude like the VP will be equals to, this should be in opposite direction, that is in negative direction. So VP will be equals to VGS off in magnitude. So that's why it is considered like the pinch off voltage is of same magnitude in terms of the cutoff voltage in case of JFET. So we can just derive that from the uh, basic equation of the current, that is Shockley equation. So this Shockley equation is in another way is also represented like ID is equals to IDSS 1 minus VGS divided by VP, but these two VGS minus VP is of uh, opposite nature. So overall the magnitude of this should be defined here. So VGS by VP, it is like it is negative and this is positive, but overall it should be such that there should be a negative sign. That means the mod will be taken care of. Okay. So this is, you can say, the modified, or you can say we can just represent ID equals to IDSS 1 minus VGS by VP whole square. Okay. So here mod will be used if you want to have the uh, if you don't want to keep the sign of VP and VGS of in relation. So this will be the case. Okay. So VGS of is the VGS when ID equals to 0, and VP is the case where ID is equals to IDSS. Okay. So you can just go with that. And now before going to have the description of different relation of different voltages, we will just go with how the current and voltages are going to be related in case of JFET. So here this is gate, this is drain, and this is source. So this voltage is VDS, and this voltage is basically VGS, and this voltage is VDG. Okay, so from there it is defined like the different voltages of the JFET is defined. VDS is equals to VDG plus VGS. So this will also be helpful for different problem solvings. Okay, and through this you can just see if this is the current, like this is the current expression, like the electrons will be moving from source to a drain in case of n channel, so the current direction will be here. But as Ig is 0 in case of field effect transistor, the gate current is almost 0. So whatever id is flowing, the same id will be flowing through the source also. So from there we can have the relation like id will be equals to is also. So whatever id is there, similar will the relation for case of the uh, source current also. Okay, we will see some of the relations or some of the parameters. So Fvt parameters we will see. So what are different parameters are there? So as here our id is going to be function of VGS. So VGS is also going to define the id because VGS, that is used as the control voltage. So VGS will be defining the id, and also this id is defined by the VDS also. If we are going to vary the VDS, there will be increase or decrease in the id value. So as we are going to increase the VDS, the id will be increasing, and after that, after some time, it will become constant. So id is function of these two. So with relation to these variables, some different parameters are defined. So these parameters are like, the one is drain resistance. So this drain resistance is defined by RD. So RD, as it is drain resistance, or we can call it the output resistance. So output resistance will be the relation of output current and output voltage. So RD will be defined as change in VDS, that is output voltage, that is VDS divided by change in output current, that is ID. So this is defined for a fixed value of VGS. Here the VGS is constant. Okay, so this is how the RD is defined, that is output resistance. The typical value of RD is between 5 kilo ohm to 600 kilo ohm, or generally its value is around 5 kilo ohm. That means very high. So the output resistance in case of FET is very high. Okay, so this RD is also called internal resistance. Internal resistance of Fvt. Okay, so this RD can be obtained either from, it can be obtained from transfer characteristics or output or drain characteristics, we can call it. So this is transfer characteristics or drain characteristics. So we will just see the drain characteristics. So in case of FPTs, we have seen the drain characteristics is this is VDS and this is ID. So as we are going to increase the VDS, it will be increasing linearly, and after the pinch off, it will become constant. Okay, so some other value is there. Suppose this is VGS is going to reduce, so it will be increasing, and then it will become constant. So this is VGS1 and this is VGS2. So for VGS1, that is of higher or you can say less negative, and this is more negative. Okay, so for reference we can just call, like suppose this is -3 volt and this is -7 volt. This is just for a reference. Okay, that means VGS1 is higher in magnitude in sign, like it is less negative and this is higher negative. Okay, so if this is the relation, so to find out the RD, we need to find out the change in current basically. So we are here at but RD is defined at constant VGS, so either of these two VGS can be considered. So what VGS1, suppose whatever change in current is there, suppose this is the point 1, and to have clear understanding we can just let me just see. So it is going to be increasing and then it is constant, so it is not constant, practically it is having some increasing value. Okay, so instead of being constant it is some increasing value. So here suppose this is the value and another current is this is under current. So this is the voltage, so this is change in VTS and this is change in ID. So RD will be defined by change in VDS divided by change in ID. So from there we can call it like, as change in ID is very less, so as the ID value is less, the RD value will be very high, and change in VDS is very high. Okay, so these both are going to make RD equals to very high. So this is how we will be defining this RD value, and the same RD can also be defined by using the transfer characteristic also. So if the graph is given or the value is given at constant VGS, we will be plotting this change in ID and then change in VDS. So from there we can get the value of drain resistance. The next parameter is transconductance. Transconductance, or it is also called mutual conductance, defined by GM. Okay, so transconductance is called transfer conductance. So this meaning of transfer is like, so conductance means it will be the relation of current and voltage, but in case of JFET we are having the only one current, that is drain current. So if drain current is there, then the voltage will be a input voltage. So input voltage is VGS. So this is basically transfer means whatever the current and voltage are there, one will be from the input side, another one will be from the output side. Okay, so here RD and V relation is going to be there, and ID and I and V are of opposite side. Okay, so transfer meaning, so here transfer means this, the I and V will be of opposite side. Okay, whenever there will be a transfer term, so the relation between the two parameters, one will be from the input side and another will be from the output side. So this GM is defined by, but it is of opposite side, but only one current is there, so ID will always be, the current will be ID, but VGS will be from the input side, that is VGS, it will voltage will be from the input side. So it will GM will be the relation. This is change in or change in ID divided by change in VGS, and this will be defined for constant VDS. So this is your transconductance parameter. Okay. So this is also defined in terms of like GM is change in ID, change in ID divided by okay. So this is so GM is defined as change in ID divided by change in VGS. Okay, and this is defined for constant VDS. Okay, so this is how the transconductance is defined. So the similar we can obtain the transconductance either by transfer characteristics or by using the drain characteristics. Okay, so it is obtained by transfer characteristics or drain characteristics. Okay, so we will just see in case of transfer characteristics. So this is your VGS, that is in negative direction, and this is your ID. So we know this is given by this relation. This is IDSS, and this is where ID is going to be 0. So this value is VGS of is defined. Okay, so uh, to find out the GM, so to find out the GM, we need to find out the change in ID. So change in ID means, so ID value, we will be taking two different values of ID. For these two different values of ID, what is the value of VGS? So this will be change in VGS, and this is change in ID. So by finding out this, so change in ID divided by change in VGS, and this is plotted at constant VDS. So this plot is at constant VDS. Okay, so this relation will be going to give us the GM. Okay, one more parameter is there, that is called amplification factor. That is very important. So this is third one is amplification factor, that is defined as the mu. Okay, amplification factor is basically voltage amplification factor. Okay, so in case of FETs, it is voltage amplification. So this mu is the voltage amplification. That means it will be the relation of output voltage and the input voltage. So output voltage is your change in VDS divided by change in VGS. But this VGS is of positive side, and this is VGS is defined like it is in negative side. Okay, so this is in negative side. It is -1, -2, -3, -4, and so on. So these two are of opposite nature. So mu is defined as negative of this, and this is defined at constant ID. So at particular ID, suppose this is the ID, whatever ID is there at this point, what is the change in VDS, and at that time what is changing? ID is there. Okay, so VGS is there. So that will be defining your amplification factor. The typical value of amplification factor is coming out to be like between 2.5 to 150. So this the maximum voltage gain of FETs is basically going to be given by this mu, that is amplification factor only. Okay, and in most of the cases uh, this mu should be varying between 2.5 to 150 range. Okay, and this mu can be obtained from the graphical data, but this will only be plotted from that only can be obtained from the transfer characteristics only. Okay, so mu is obtained only from transfer characteristics. Okay, so if we see the relation, we can rearrange the parameters like mu is equals to, this is change in VDS and change in VGS. If we apply the concept like it is change in ID and change in ID, if we multiply it, we can get this is going to define us the RD, and this is going to define as the GM. So from there we can just correlate, like if we just neglect the sign, we can see like, so mu will be given by like RD multiplied by, this is your GM. So your amplification factor will be multiplication of RD and GM. Okay, so GM is one of the main parameter in case of FETs, basically transconductance. We will be going to find out the expression for GM, that is transconductance. So we know ID is equals to ID SS 1 minus VGS by VP to the power 2. Okay, so this is the current equation in case of JFET. We need to find out GM. So GM is defined by like change in ID divided by change in VGS. Okay, so we will be just differentiating this ID equation in terms of VGS. Okay, so if we are going to differentiate, it will be del ID by del VGS will be given by IDSS. So this is VGS, so it will be going to be differentiated, that means it will be 2 times of 1 minus VGS by VP, and then differentiation of this, so it will be 0 minus, it will be, once we are going to differentiate it, it will be 1 by VP. Okay, so by rearranging we can just see, so this will be nothing but the GM, it will be minus 2 times IDSS, and this is divided by VP 1 minus VGS by VP. So this is the expression of GM. This is the basic expression. Okay, and the unit of GM will be, because it is current divided by voltage, so it is not like ohm, it is really 1 by ohm. Okay, so it is 1 by ohm, or also called as opposite sign of ohm, that is, it is called Maho. This is ohm and this is Maho. Okay, so this is the unit of GM that is going to define the transconductance. some other equations of GM is also there. You can just go with putting the value of, like, if we are in from the current equation, we can put 1 minus VGS by VP, and we can replace this 1 minus VGS VP from the current equation, so we can get the GM in terms of the current. Okay, so there are different equations, like different relation of GM you can just go with. So I will be writing the equations. So that will be GM is also defined like minus 2 by VP under root ID into ID SS. So once we are going to replace this 1 minus VGS by VP by putting the relation of ID and IDSS, we can get this relation for GM. Okay. So this is, I think, basics of JFET in terms of their mathematical analysis, like the equation. So all voltages and currents of JFET can be defined by using the Shockley equation. So based on these formulas, most frequently the numericals are asked in either in GATE or also in different competitive exams also. Okay, so these parameters or these equations you can just uh, remember. So I think this is basic of JFET. Their mathematical analysis and different parameters we have gone through. Okay, so you just need to remember this current equation. Once we know the current equation, from there we can differentiate this current equation in terms of VGS, and we can get the GM value. Okay, along with that, there are three different parameters we have gone through. That is drain resistance. Okay, the drain resistance is nothing but the input resistance. Another one is transconductance, that is GM, and the next is amplification factor. Okay, so this is I think all about JFET. So the next point we will see into the our next class, that is MOSFET. So from the next class onwards, we will be starting with the basics of MOSFETs. Okay. So I think we can just, yes, anyone is having any doubt, you can ask.